Alright, what's up guys? In this video we're going to pick up with our integration practice part 2. In this video we will solely be focusing on evaluating integrals using integration by parts. If you missed the last video I did a video where we evaluated some practice integrals using the method of use substitution, and so I did a video for that that's posted on the Facebook page if you didn't see it. And so that one's there. And then today, in this video, we're going to do integration by parts. All of the integrals that we're going to do today will require integration by parts in this video. So there's going to be no ambiguity about what method that we're going to be using. Really what I'm more trying to do in this video is to try to explain what's the appropriate U and DV to pick and all that kind of stuff before, so you can get your the correct answer. So that's what we're going to be doing today. Alright, so let me just briefly introduce you to integration by parts. I'm not going to talk too long on it because I don't want to hold you too long, but I just kind of want to mention a few things. So basically, integration by parts is derived from that product rule that you learned in first semester calculus. And it's specifically helpful when you have a product of functions. It's one of those methods that I think is a little bit more involved than a use substitution. I do a use substitution over by parts any day, but all integrals can't be evaluated using use substitution. I just want to mention a few things to you. The first thing is, if you're ever in a situation, it's a dilemma, and maybe you don't know what's the appropriate method to use, because let's say you get an integral and it looks like use substitution, or if you're not sure if it's by parts or not, the general rule of thumb is to try use substitution first. Excuse me. And if that doesn't work, then try by parts. Now you probably say, well, how if I know it wasn't work? Because I just talked about in the last video, it's a whole heck of a lot easier to tell when a use substitution is not working, or you've picked the wrong method or the wrong U or whatever, as opposed to integration by parts. And the reason for that is, I mentioned this a couple days ago in the video that we did. A lot of times in integration by parts, when you are picking the U and the DV, a lot of times you'll get a situation where you may have to use integration by parts twice on the same integral. Some integrals can be more than that. This typically happens when you've got exponentials multiplied by, let's say, some trig function in there, or if you have something of a high power that needs to be brought down, then you may have to do integration by parts twice, or more times than that. And the reason why I wanted to bring that up is because I don't want you to assume that you probably picked something that was incorrect. I mean, certainly you could have picked the wrong thing. I mean, you might have picked something to be U that you should have picked and that to be DV. You know what I mean? So I'm not saying that can't happen, but I don't want you to assume that your selections are going to be wrong in some cases. It's just going to be a situation where you will have to use integration by parts twice, sometimes multiple times to get an answer. And I just wanted to mention that to you. Professors are really good for throwing tricky ones on there like that, where you have to use the method twice. So it's not uncommon to have to go through the problem using by parts twice. So I just want to make that aware to you. It doesn't mean you necessarily picked the wrong thing. It just means that that might be the nature of the problem. But again, this all kind of comes down to practice. The more you practice, the easier it'll be for you to make appropriate selection. And then if it does, you do end up getting, having to do it again, you're a little bit more sure of yourself. All right, so that's just a little background on integration by parts. So let's take a look at the integral. So for the first one, we have x times e to the negative x dx. Like I said, we already know what we're going to be doing. It's integration by parts. Now, if you don't know integration by parts formula, it's imperative that you try to at least memorize this, or when you get to class, maybe write it down before a quiz or test or something like that. You have to memorize the formula for it. The formula for it is the integral of u dv is equal to uv minus integral v du. So when you do this method, you're going to get a new integral out that you're going to have to integrate. it's imperative for you to know this definition, because once you make the appropriate selections, you then have to pull the information back into the formula, okay, and integrate again. So if you don't have the formula memorized or at least written somewhere, you wouldn't be able to solve an integral using this method. So I think the best thing to do is probably just say it over and over again. That's how I did it. I think if you're a math student or a physics student that has to take a ton of calculus, a lot of this stuff is going to be stuck in your head from the onset, because you're already going to be taking a lot of classes that's going to require you, not necessarily integration by parts. I mean, I'm pretty sure that might come up some time or two where you have to use this method, but you're going to be using calculus a lot. So a lot of this stuff is going to just kind of stick with you. This tends to happen with the math majors, obviously, but even the physics majors, because you're going to be taking so much math, you're going to be using this stuff all the time. So a lot of this stuff is just going to get stuck, as opposed to maybe, let's say, a bio major or so, who, they don't have to take a whole bunch of math, might not retain a whole lot of this information because they don't actually need it, unless in specific circumstances. So what you do for by parts is you select a U, and then you select a DV. Now, the question is, and it's a kind of a unfortunate question, the question I get all the time, and I'm pretty sure professors get this question: how do I know what to pick U and DV to be? Much like I talked about in the last video with the U substitution, it comes down to practice. The more you practice, the easier it's going to be for you to determine what's the appropriate selections. So that's unfortunately the first thing I had to tell you. It kind of just depends on the integral, in a sense. However, there is an acronym that you can use that may provide some assistance to you, and it's called LIATE. If I'm pronouncing that wrong, somebody please let me know. I don't know how to pronounce it, but I know what it means. And LIATE stands for logs, inverse, algebraic, trig. And when I say trig, I'm talking about trig functions, trig, and then E is exponential. Okay, so how does this work? Well, here's the thing. When you look in your integrand, you use this acronym here, and whichever appears first in the in your list here, that you see first in the integrand, based on which one is that you identify first, then you will need to use U to be whatever that is. Like, for example, in the integrand, I see an X here. Well, we classify X as algebraic on this using this acronym. So since there is an algebraic in there, so to speak, it would be wise if you picked U to be probably X. This will work 96% of the time. It's been very helpful for me. However, again, it just comes down to practice. And so this isn't going to help you all the time, but it is a really, really good thing to look at. It might not even help you that much percentage. I think I over-exaggerated on that. But it's just come down to practice. And so if we're basing it on that, I would select you would probably select U to be X. If I were just integrating this on my own, I would select U to be X. So I'm going to do that as well. So I just pick U to be X. Another great thing about integration by parts is that once you've identified what U is, DV is everything you didn't pick. Right? So as you see in the integrand here, we have X times E to the negative X dx. If we pick X to be U, then that must mean that what's left in there, it must be DV. Right? So that means that DV is just E to the negative X dx. Okay? That's pretty much the steps for that part. So this will be helpful. It's something good to use. Make sure you memorize the formula. And yeah, that's all you can do. For by parts, it's going to be, because I talked about this in the last video with the U substitution, by parts is different. So a lot of times you can't always visualize what's going to come out, because don't forget that you have to integrate a second time. So it's kind of hard to predict what the answer is going to be. You understand? Because it's just a little bit more involved than a U substitution, where I can actually look at it and say, okay, if I pick this to be U, this will cancel, this will happen, blah, blah, blah. By parts, not so much, because there's a lot going to be going on and you have to integrate again. So it's very difficult a lot of times to just determine what the solution is going to be. So you're not going to have that loophole anymore. So that's why it's key to practice. So the next thing you do is you find du, and I'll talk about that. So du just means derivative of u, which you guys know. That's just 1. And then v. What is v, right? Well, to get v, you integrate dv. So that means that's the antiderivative of e to the negative x dx. That's what v is. You integrate dv. Whatever it may be, you integrate that. So what you do with by parts, you pick a u to differentiate and a dv to antiderive. And that's how you go about it. As I mentioned at the beginning, don't be surprised if you have to, do the method twice. That will happen, unfortunately, with by parts. So now what you do is you take the formula and you sub in the appropriate information on this side. Okay. And then you have to integrate this side over here. So I just use brackets to kind of do it. So what we'll have is x times, oops, I'm sorry, we forgot to integrate e to the negative x. The antiderivative of e to the negative x is negative e to the negative x. Sorry about that. Okay, so now we've done that. That's going to be negative e to the negative x. That's an easy one. And then it'll be minus the antiderivative of negative e to the negative x times 1, and then that's dx behind it. And then, you just simplify it down a little bit. And if you do that, if you want to rewrite this left-hand side, you're not going to mess with it much after that. You can bring the negative in front. So you'll have negative e to the negative x times x. And then you'll have minus antiderivative. 1 times negative e to the negative x is negative e to the negative x. And then you get dx. And now you have your new integral to integrate, which is this one here. So we go down here and we do negative e to the negative x dx. That's what we need to integrate here. All right, so what's the answer to that? Well, remember when we were up here, remember that the antiderivative of e to the negative x dx was negative e to the negative x. So if I were to reverse that, I would just get e to the negative x. So the answer to that is just e to the negative x. I'm sorry, this is supposed to be an x, by the way. Is e to the negative x. And all you do is you don't do anything with the left-hand side. Once you've simplified it, you just take this solution and basically put it in the formula. One thing I want to mention is you do have to be careful, because remember in the integration by parts formula, we have a minus there, right? So if you end up getting something negative out when you integrate the second time, you got to pay attention to your sign changes, because 2 negatives will give you a positive and it will change. We don't have that in this situation, but it can happen. So just be aware of that. So your final answer for this is just negative e to the negative x times x minus e to the negative x and then plus c. And it's final answer for that one. So by parts is a more difficult method in my opinion, because a lot of times you just end up getting something out that is far more difficult than what you started with, and it doesn't necessarily mean you picked the wrong thing. Take a drink of water. This might be the nature of the integral. So that's the first one. By parts does require a significant amount of work to get the solution, so we're not going to go through a whole bunch of examples. I just have 4 that I want us to go through, just to kind of get your feet wet with this stuff. Let's go to the next one. Hopefully it won't take us too long. All right, let's move on to number 2. Okay, we already know what method we're going to be using. Question is, what do we pick? So also when you're doing, obviously I would love for you to practice on your own time, but if you're on the test and or even if you're practicing on your own time and you're just going through and doing integration by parts examples, just continue to write the formula all over again. That's another way to memorize it, is to go home, do some practice problems, and then every time you do it, you just continue to write it down. It'll get stuck in your head, trust me. So remember that the formula for the integration by parts is the integral of u dv is equal to uv minus the integral v du. Okay, so remember, you have to know that. And we go through the process that we went through with the last integral. So if you want to, you can use light here to determine maybe what may be the best u. If that's how you have to start by using that, nothing wrong with that. As you get better at this, you won't need that acronym. But as a starter, there's nothing wrong with using it. So if I were going to do this, I would pick u to be ln of 2x. And the reason why I would do that is because integrating ln of 2x is just going to be too much work. So I'm not picking that. Ln of 2x is easy to is easier to differentiate than integrate, and x is obviously easier to integrate. So I would have just picked x to be, or I picked dv to be x. So again, once you identify u, dv is what you didn't pick. And don't forget to tackle the dx back on the outside there. Then we go through the process that we did last time. So we find du, which is just a derivative of this. So remember, the derivative ln of 2x is just 1 over x. And then remember, for v, it'd be the antiderivative of x dx, which gives us x squared over 2. And so now hopefully you're seeing the benefit of picking u to be ln of 2x and dv to be x, because it would have been a nightmare trying to integrate ln of 2x. You don't want to try to do that. And even if it's not difficult, it requires far more work than integrating dv, where it's x. So, alright, so once you've done that, you go through the same process. You can do integration by parts with definite integrals. I don't have a definite integral in this video. I just focused on indefinites. I'm going to do a separate video for by parts with definite integrals, but I kind of just wanted to focus on indefinite in these videos. So none of these are going to have limits. So, okay, so now that you've gotten all the information, you just plug things in. So I'm going to kind of kill two birds with one stone, and I'm going to simplify at the same time. The left-hand side. I'll leave the right-hand side alone to show you how to do that. So I'm just going to write the right-hand side over, or left-hand side over here as 1/2 x squared times ln of 2x. And then over here, I have the antiderivative of x squared over 2 times 1 over x, and then dx goes behind that. We simplify this side. So you just have your left-hand side. And then over here, we'll have the you just need to slip this side over here. So x squared over 2 times 1 over x, that's just going to be x over 2. And then you got to tackle the dx over here. And that's what you do. Then you integrate that. So you have the antiderivative of x over 2 dx. Right? That's just going to be x squared over 4. Let me show you why. What you would do is you would remove the 1/2, and then what you'd end up having is basically x to the second over 2, because you would apply the power rule. 1 times x squared is x squared, and then 2 times 2 is 4. So that's why it's x squared over 4. Okay. So again, here we have a positive x squared over 4. So, we don't have to worry about any sign changing there, but that can happen, as I mentioned. So you just put everything together. Once you've taken care of the left-hand side, when you start, you don't really mess with that side ever again. You kind of leave that alone. You're just more focusing on this side. So take care of simplifying that first. So we just put the two pieces together. So we'll have 1/2 x squared ln of 2x minus x squared over 4. And then you do got to add plus c. All right, so we got 2 more we're going to run through. We're not going to do too many because this, by parts, is more involved than sub. All right, so we got 2 more. Let's see if we can work through these. All right, so we got another one here. We got antiderivative of 2x times e to the x dx. Again, we already know what method. Another key aspect is that if you're, obviously you have a product of functions, but if you see 2 different functions being multiplied together like that, it's probably going to give you a little bit of a hint. So again, keep writing it down. U dv is equal to uv minus integral v du. The more you write it down, the more you practice it, the quicker it'll get stuck in your head. Excuse me. So we go. And much like we did last time, we just, go through and try to figure out what's the appropriate thing to pick here. So again, if you wanted to use the acronym LIATE again, you certainly can. Again, you can use that, and it'll be very helpful to you. Me personally, if I was looking at this, to be honest, neither way looks any different to differentiate or anti-derive, to be honest. But if I were going to use the LIATE rule or the LIATE acronym that I showed you guys a few minutes ago, I would probably pick U to be the variable, which is the x. And oh, I'm sorry. What I did was I kind of did it subliminally, and I didn't write it. I've removed the 2. I brought the 2 outside. I'm sorry about that. I forgot to mention that. I kind of did it in my head. So what I did was I just took it out. So I had 2 times x e to the x dx. Sorry, I removed it. And as I mentioned, I'm going to pick x to be u, and then dv is e to the x. To be honest, as I mentioned before, whether I would have picked that one to be dv or that one to be x, and this one to be x, neither one of those are sufficiently difficult to differentiate or anti-derive. But I think the best option would be x for u and then e to the x for dv. That's just the way that I think about it. Then we go through and we do du, and that's just 1. And then remember, v is the integral of dv. So that's the antiderivative of e to the x dx, which is obviously e to the x. Now, the ones with the exponentials in it are always the easiest ones, for the simple fact that everybody loves exponentials because we know what the derivatives are. Derivative e to the x, e to the x. Antiderivative e to the x, e to the x. So people tend to like working with the exponentials because they're just so easy to remember. I mean, sure, you need to know some properties or whatever, but for the most part, you'll be good to go with that. So we just do like we did for the last problem. You just set everything up. So what we'll have is e to the x times x minus antiderivative of e to the x times 1 dx, which would just give me e to the x, and then dx goes behind it. You then have the antiderivative of e to the x dx, which we know is e to the x. And so all we got to do is take that 2, and we tackle that on the outside of the parentheses, and we just put these pieces together. It is a positive e to the x, so the minus can stay, and you'll have e to the x times x minus e to the x, and then if you want to, add a plus c. Is this an appropriate answer? some professors may let you get away with leaving it like that. I wouldn't. Just distribute the 2. Don't take any chances. It's not nothing too difficult to do. So just distribute the 2 to lessen the likelihood of you not getting full credit. So I just distribute it in there and just, you know. Okay. And that would be the answer. All right. We got one more and then we'll be done. So let's see if we can get through it. All right, what about this one? Oops. Sorry, trying to fix it. Okay. So what about this one here? So again, by parts. Integral u dv is equal to uv minus integral v du. Okay, so you just need to determine what's the best thing to pick, u to b and then dv. Okay, so if you want to use the acronym, you certainly can. I picked, in the last problem that we did, I think it was problem number 2, I picked ln to be u, and I'm going to do the exact same thing here. So I'm going to pick u to be ln of x. Well, all that means is that dv is what's left behind. Notice I just have an x to the 11th at the bottom. There's technically a 1 there. In a fraction like that, it never remains. There's just never not nothing there. It's just a 1. So I would just write this as 1 over x to the 11th dx. And then we go down here and we got du. Well, okay, well that's just 1 over x. And then for v, we integrate dv. So that's the integral of 1 over 11x. Oh, excuse me, not 11x. 1 over 11 dx, basically. Okay. And you just go through and you integrate that part. So that's just first semester calc. I'm pretty sure you guys know how to integrate that. That's just negative 1 over 10 x to the 10th power. And now we have all of the information we need to plug it in there. So I'm going to simplify. I'm going to bring the negative to the front. I'll have ln of x all over 10x to the 10th power. And then it'll be minus the antiderivative. Negative 1 over 10x times 1 over x. That'll just end up giving you negative 1 over 10x to the 11th power. So that'd be 1 over 10x to the 11th power. And it is negative. So I tackle that out there. And then you do that part. You integrate that. So that's negative 1 over 10x to the 11th. And you integrate that with respect to x. Okay, well, if you integrate that, that'll just end up being negative 1 over 10. Make sure that's right. No, I'm sorry, that's not right. This ended up being negative 1 over 10. I'm sorry, not negative 1 over 10. Negative 1 over 100 x to the 10th power. Sorry, I got a little cut up there. Now, why is that? Well, here's what I did. I took a 1/10th out. Removing that essentially just left me with what we originally had before, which was the 1 over x to the 11th power, which gave us the negative 1 over 10x to the 10th. And so basically all I did was I just multiplied by that. That was to the 10th power. And of course, and this actually shouldn't be negative, should be positive because it's 2 negatives. Yeah. Okay. And so what I got here was 1 over 100 x to the 10th power for that. And then to get the final answer, we just put the pieces together and it'd be negative ln of x all over 10x to the 10th minus 1 over 100x to the 10th power. And then you just add a plus c. that is how you do integration by parts. So I hope this video was helpful. I just wanted to go through a few examples to help you out with this. But if you have any questions, ask me at any time. I'll be more than happy to respond. I'll see y'all next time.